The story of the diesel engine rightly begins with an early chapter in the history of fire. Long ago, the people of southeastern Asia made using an ingenious device called the fire piston or fire syringe. This consisted of a hollow tube, closed at one end, and a round stick that fitted snugly into the tube. Tinder was placed at the bottom of the round stick. Then when this stick or plunger was inserted into the tube and driven down quickly, the tinder took fire and burned. Let's see what happens inside this fire-making apparatus. As the round stick or plunger moves down the tube, the air in the tube is trapped, squeezed into a smaller and smaller space. Finally, the tinder at the end of the plunger ignites. To understand how this happens, let's construct a modern fire syringe. First, we turn the apparatus upside down. Then we put two thermometers in convenient places. One of these thermometers will record the temperature of the air inside the cylinder, and the other registers the room temperature. Next, we add an instrument for measuring the air pressure in the cylinder in pounds per square inch. With the piston in the down position, the pressure gauge on our apparatus reads 0, and both thermometers are at room temperature, 74 degrees. We start compressing the air. As the piston goes up, the pressure rises. The temperature outside the cylinder remains the same. But inside the cylinder, the more the air is compressed, the higher the temperature goes. Now the air in the cylinder is hot enough to boil water. Higher and higher go temperature and pressure. Now it's hot enough to melt tin, until finally the air is squeezed into about 1/16 of the space it occupied before we started compressing it. At this point, the pressure and the temperature of the air within the cylinder are both extremely high. So high that a mist of oil sprayed into it will take fire and burn. This shows us that highly compressed air gets hot enough to ignite fuel oil. This principle, called compression ignition, was first developed by Rudolf Diesel. Now let's examine another phenomenon. We stretch a piece of rubber sheeting over the mouth of a container and place the container over a flame. As the rubber sheeting puffs out like a balloon, we see that air or gas expands when it is heated. Now let's see how this principle applies to our apparatus. First, the air in the cylinder becomes hot from compression. Then the burning oil raises the temperature still higher. This additional heat causes the gases to expand, forcing the piston down. Now let's convert this apparatus into a mechanism which will apply these principles of compression ignition and expansion to provide usable power. First, we take away the pressure gauge and the thermometers and strengthen the walls of the cylinder to withstand continued high temperatures and pressures. We also need a couple of pipes or manifolds, one to bring fresh air into the cylinder, the other to carry the burned gases away, and two valves to seal the air in the cylinder while it is being compressed and while the oil is burning. Next, we install a better atomizer, which we shall call the fuel injection unit. Then, in order to transform the up and down motion of our piston into more convenient rotary motion, we change the piston rod to a connecting rod and add a crankshaft. And finally, to support our mechanism, we add a housing and a base. Now let's see how this engine works. First, the intake valve opens, and as the piston moves downward, fresh air is drawn into the cylinder. Next, the intake valve closes, tightly sealing the air in the cylinder as the piston moves upward on its compression stroke. The fuel injection unit sprays fuel into the highly compressed hot air. The oil burns, and temperature and pressure increase enormously, driving the piston down. The exhaust valve opens, the piston moves up, and the gases resulting from combustion are forced out. This engine is called a four-stroke cycle diesel engine. One of every 4 strokes is a power stroke. Intake, compression, power, exhaust. Intake, compression, power, exhaust. These 4 strokes of the piston occur every 2 revolutions of the crankshaft. In the 2-stroke cycle engine, the functions of intake, compression, power, and exhaust are performed in 2 strokes of the piston. This can be accomplished in several ways. In one, the intake valve of the 4-stroke cycle engine is replaced by a row of openings in the cylinder wall. These are called intake or scavenge ports, which are supplied by a manifold with fresh air under pressure. Suppose this cylinder is full of fresh air. The cycle begins with the piston moving up. The air is compressed, and the resulting high temperature causes the fuel charge, injected near the top of the stroke, to ignite and burn. The combustion gases expand, forcing the piston down. As the piston nears the bottom of the stroke, the exhaust valve opens, allowing the burnt gases to escape. Then the piston uncovers the scavenge ports, and fresh air blows out the remaining gases. The exhaust valve closes. The piston moves upward, covering the scavenge ports and trapping the fresh charge of air in the cylinder. Thus, the 4 processes of intake, compression, power, and exhaust are completed in only 2 strokes of the piston. Hence, every 2nd stroke of the piston is a power stroke, 1 power impulse to each revolution of the crankshaft. The large Winton diesels used in some of our new submarines are of this type 2-stroke cycle engine. In another type of 2-stroke cycle diesel, the exhaust valve also is replaced by ports in the cylinder wall. These exhaust ports are located opposite and slightly above the intake or scavenge ports. Suppose the fuel has been injected and ignited by compression. Due to the added heat, the combustion gases expand, driving the piston downward. As it approaches the bottom of the cylinder, the exhaust ports are uncovered, allowing the exhaust gases to escape. The piston continues downward, uncovering the scavenge ports. Fresh air, called scavenging air, is forced through these ports, blowing the remaining exhaust gases from the cylinder. The piston then passes through the bottom of the stroke. A fresh charge of air is trapped and compressed as the piston continues the upward stroke. Theoretically, a 2-stroke cycle engine should produce twice the power of a 4-stroke cycle engine of the same bore and stroke, since it does the same work in half the time. In practice, however, other factors reduce this 100% increase to an actual figure of 70 to 80%. For instance, the loss of power resulting from the uncovering of the ports before the piston reaches the end of its power stroke. Also, the factors of less perfect scavenging and the diversion of power to drive the air pump. When we apply the 2-stroke cycle principle to both ends of the piston, we have what is known as the 2-stroke cycle double-acting engine. The large Hamilton MAN engines in many of our new submarines are of this type. In this design, combustion takes place on both ends of the piston. The piston is connected to the crankshaft by a piston rod, a crosshead, and a connecting rod. To prevent the escape of combustion gases around the piston rod, it passes through a stuffing box. There are 4 rows of ports in the cylinder wall. The 2 center rows are for the entry of scavenging air. The 2 outer rows for the escape of exhaust gases. Injection valves for the injection of fuel oil are located at each end of the cylinder. Let's start the cycle with the expansion of the combustion gases in the upper cylinder. The piston is driven down, first uncovering the exhaust ports, and the exhaust gases start to escape. As the piston uncovers the scavenge ports, the scavenging air sweeps out the remaining burnt gases, filling the cylinder with fresh air. The piston moves up, covering the scavenge ports. At this time, a rotary valve restricts the exhaust passage enough for the scavenging air to build up pressure in the cylinder. The piston compresses the air as it continues its upward movement. The fuel is injected near the top of the stroke. Combustion takes place, and the cycle is repeated. The same process takes place in the lower cylinder, the power stroke occurring at the same time as the compression stroke in the upper cylinder. Thus, each stroke of the piston is a power stroke. Consequently, the double-acting engine develops about 70% more power than a single-acting 2-stroke cycle engine of the same weight and dimensions. The opposed piston engine, like the double-acting engine, commonly works on the 2-stroke cycle principle. This large Fairbanks Morse engine, used in our submarines, is an example of the opposed piston type. In this engine, there are 2 pistons in each cylinder, connected to separate crankshafts. The 2 crankshafts are connected by gearing, a chain, or a vertical shaft with bevel gears. There is a row of ports at each end of the cylinder. Usually, the scavenge ports are at the upper end, and the exhaust ports at the lower. As the pistons move inward, they compress the charge of fresh air between them. At the inner point of the stroke, fuel is injected into the combustion space between the pistons. Combustion takes place, and the pistons are driven apart by the high-pressure gases. The exhaust ports are uncovered by the lower piston, allowing the gases to escape. Then the scavenge ports, uncovered by the upper piston, admit fresh air to blow out the remaining exhaust gases, and the next cycle begins. The lower crankshaft is advanced about 15 degrees so that the exhaust ports are opened and closed before the scavenge ports. The opposed piston engine develops about the same power as the double-acting engine of similar bore and stroke. In all the various types of two-stroke cycle engines, the functions of intake and exhaust are mainly performed by an air pump or scavenging air blower. A typical example is this model, called a multiple lobe positive displacement blower. Inside an airtight housing, two rapidly turning impellers trap the air between their lobes and the wall of the housing, discharging the air at a pressure of 2 to 5 pounds per square inch above atmospheric pressure. These helical lobed impellers are designed in this manner to deliver a uniform amount of air and to reduce noise. They are machined and finished to very close tolerances on machines especially designed for this purpose. There are several types of scavenging systems in two-stroke cycle engines. In most scavenging systems, the air passes through a silencer before it enters the blower. In all of them, the fresh air is forced into the cylinders by the blower through a pipe called the scavenging air header. In the Uniflow system, the scavenging air flows directly through the cylinder from one end to the other. In the loop system, it flows around the cylinder in a loop, entering and leaving on the same side. In the direct method, the scavenging air enters at one side of the cylinder and leaves on the opposite side. The purpose of supercharging is to step up the power output of the engine. Every particle of fuel requires a certain amount of air for complete combustion. By increasing the density of the air charge at the beginning of the compression stroke, more fuel may be injected and burned, thus increasing the power output. The four-stroke cycle engine is supercharged by forcing air into the cylinder under a pressure of 5 to 12 pounds per square inch above atmospheric pressure. This increase in the density of the air charge results in higher combustion pressures and consequently more power. Some two-stroke cycle engines are supercharged by trapping air in the cylinder at scavenge air blower pressure. When valve scavenging is used, the exhaust valves are timed to close before the scavenge ports are covered by the piston. This timing increases the pressure of the air before compression by 2 to 5 pounds per square inch above atmospheric pressure. In the double-acting engine with loop scavenging, a rotary valve is provided for supercharging. This revolving supercharge valve in the exhaust passage is timed to close shortly after the piston covers the scavenge ports. Thus, scavenging air pressure is maintained until compression begins. The opposed piston engine is supercharged by setting the crankshafts so that the lower piston leads the upper. Because of this so-called lower crank lead, the exhaust ports are covered ahead of the scavenge ports. This permits the scavenging air to continue entering the cylinder after the exhaust ports are covered. Hence, the air in the cylinder is supercharged to the scavenging air pressure. There are two general methods of injecting the fuel into a diesel cylinder: the air injection system and the mechanical or solid injection system. The air injection system utilizes high-pressure air to force the fuel into the cylinder through the nozzle of a spray air valve. This breaks up or atomizes the fuel into a fine spray. To overcome the high pressure within the cylinder, an air pressure of 600 to 1,000 pounds per square inch is required for injection. This high-pressure air is usually supplied by a compressor of the multiple tandem stage design, in which the air is compressed in steps or stages. The Nelsico engine, installed in a large number of S-type submarines, for instance, uses a three-stage air compressor of this type. Each piston has two steps, and the air is compressed in three stages. The first stage compression takes place in the large cylinders. The second and third stages of compression take place in the two cylinders above the first stage pistons. Circulating seawater coolers are provided after each stage to carry away the heat generated by compression. After the final stage, the compressed air is carried to the spray air valves. The fuel is applied to these valves by a pump of this type. This pump consists mainly of a plunger working in a cylinder, a discharge valve, a check valve, and a suction valve to control the volume of fuel pumped. The plunger and the suction valve are operated by a cam and tappet arrangement from the engine camshaft. The discharge valve is held closed by a spring and opens under oil pressure. As the plunger moves outward, the suction valve opens and fuel oil is drawn into the pump chamber. Through the first part of the plunger's pumping stroke, oil is returned to the supply chamber as the suction valve is gradually closed by the tappet arrangement. When it is completely closed, the remainder of the pumping stroke forces the fuel up through the discharge valve into the line leading into the spray air valve. The point at which the suction valve closes is controlled through the lever and tappet arrangement by the engine throttle or the governor. The length of the effective pumping stroke is thus regulated so that only the required amount of fuel is pumped into the spray air valve. The air from the compressor and the oil from the fuel pump are piped to this typical spray air valve. The fuel enters the chamber surrounding the valve stem. This chamber is filled with spray air at a pressure of 200 to 500 pounds above the pressure in the engine cylinder. When the valve stem is lifted, this difference in pressure blows the fuel through the nozzle into the cylinder in the form of a fine spray. The mechanical or solid injection system requires no high-pressure air. The fuel itself is under pressure great enough to atomize and inject it into the cylinder. The primary units of this system are a fuel injection valve and a fuel pump. Most of the diesel engines in the submarine service have an individual fuel pump and an injection valve for each cylinder. The fuel pumps for an engine may be separate, or they may be grouped together in a common housing. The Bosch fuel pump, used on the Fairbanks, Morse, and Hamilton MAN engines, has a plunger and a barrel, and a discharge check valve. The effective stroke of the plunger may be adjusted for different engine loads by a rack and gear, which rotate the plunger. The plunger is driven off the camshaft. When an engine piston nears the end of its compression stroke, The pump for that cylinder forces a measured amount of fuel up to the injection valve. The oil pressure opens the injection valve, and the oil passes through the injection nozzle into the cylinder. Another type of mechanical injection system combines the pump and the injection valve in a single unit. This type, used on the Winton diesel engine, is called the Winton unit injector. This injection unit consists of a plunger, a gear and rack, a needle valve, and a spray tip. The rack and gear rotate the plunger, changing its effective pumping stroke and thus controlling the quantity of fuel injected. Fuel oil fills the barrel below the plunger. The fuel is forced down by the plunger, and when enough pressure has been built up, the needle valve is lifted from its seat. The fuel is thus forced through the tiny holes in the spray tip into the cylinder. The degree of atomization is determined by the velocity of the fuel through the spray holes. At the full speed of the engine, the oil shoots from the spray tip of this injector at 13 miles a minute, a velocity greater than that of sound. The fine atomization of the spray ensures prompt ignition and complete combustion, vital features in the efficient operation of the diesel engine.